Okay, so we had talked about the trapezoidal rule and Simpsons rule, or Simpsons 1/3 rule. Trapezoid rule was OH squared, and Simpsons rule was OH to the fourth, and which is kind of nice. And let's go ahead. Oh, we did try to derive the Simpsons rule on two intervals. We set up the Lagrange integration interpolating formula. Then we did some substitutions and integrated. And it turned out to be, after some calculations, that we got the formula that we wanted to start off with. Okay, so you can derive it using an interpolation formula. The other way you can derive some things are in terms of Taylor series. Trapezoidal rule is degree 1, so if you have linear functions, it's exact. Simpsons rule exact through degree 3. And we showed that if you integrated like from 0 to 2 of a cubic polynomial, all you have to do is evaluate it at 0, 1, and 2 at this 1, 4, 1 rule, and you get the exact answer, which is kind of nice at times. But Alex didn't do it on his math seminar or math stats test, but that's okay. I would be impressed, but I'm still impressed with all of you, so you don't have to do those things on math stats test. We also showed you how to derive the error in Simpsons rule by setting up the Taylor series expansion here with 1h and 2h, finding some linear combination so it cancels out the f of a, the f prime of a, the f double prime of a, and f triple prime of a. And if you do that with h over 3, 4h over 3, h over 3, again, notice this 1, 4, 1 business. And if you subtract, you get the formula equal to the other side, and they're approximate to each other. And so, and use the second fundamental theorem of calculus and get this same sort of idea using the Taylor series error. So both those interpolating formulas and the Taylor series helps out in developing new formulas as well. There's also, your book talks about the 3/8 rule. When the number of points is even, so 1, 2, 3, 4, but your intervals are odd, you can use the third order equation that you can use in the book. This is an important formula. Remember that you can decrease your width of each subinterval and have more and more subintervals, but eventually you hit a law of diminishing returns and that the propagation of error kicks in. So smaller and smaller intervals theoretically should give you more and more accuracy, but at some point the propagation of error and round-off error takes in and your error does not decrease anymore, it actually starts to increase. Anyway, that's an important idea. You might just make a mental note of that idea. Also, think of field hockey or hockey, whichever one you do. Now, and we talked about you can even derive better Taylor series representation. There is something called the Boole's rule, where you take 7, 32, 12, 32, 7 of your weight and divide over 90, and now that's OH sixth, which you can get more and more accuracy given a subinterval. Just get the right weighted average. And if we have unequal length segments, that's where you have to adjust. You might have to do 3/8 on one side, 1/4 on the other side, 1/8 on the other side, and other things. So that's not such a great thing. So again, you try to break the integral into pieces and use the various ones on those subintervals. And then multiple integrals, what you can do is you have sort of all these data points. You can use on each slice, use the trapezoidal rule or Simpsons rule on that, and then you get subintervals. And then you could do the Simpsons rule on those subintervals. And just because we've been talking about a math stats, it's very much like marginal probabilities, and then find the expected probabilities on the side. All right. Let's not play this game. Remember that if your concavity is much greater, if you have a strong cavity, then you're going to get a lot of error. That's why the OH squared gets quite a bit larger in a trapezoidal rule. If you have sort of a flattened kind of curve, then your error is much smaller. Here's a trapezoidal rule again. Here, if you just get unfortunate and take these 2 points, you get a lot of extra error that you missed. But with the trapezoidal rule, you got just those points. So it does depend on the function whether or not you work okay. You can program it, and there are the formulas for Simpsons and trapezoidal rule. And okay, let's now talk about the fundamental theorem of calculus, which is just an amazing theorem that you can find the area under the curve just by evaluating 2 points. Of course, you have to do the antiderivative, but all you have to do is evaluate 2 points, and you find the area under the curve or the signed area under the curve. That's just amazing. But our very important Gaussian, the normal distribution, there's no nice antiderivative for this. It cannot be integrated. There's no closed form for this. So what do? So that's where some other things come in. But before we do that, let's try to have you do this problem. Let's determine a value of n that will approximate that integral from 0 to 1 of the square root of 1 plus x squared dx with an error of less than 0.01. Okay? So at least tell me a strategy that we could use for this.
Isn't there something with substitution with sign that we can do? Or is that minus x squared?
It'd be something with tangent squared and secant squared. I'm trying to do something nicely where we just use a trapezoidal rule for this. How do I find out the number of points that I would use for trapezoidal rule? But I think you are right. It's just trig substitution.
Well, we probably need to look at the formula for the error of a trapezoidal rule.
Okay, so the formula of trapezoidal rule, it is OH squared, right? So we'll need to know what the second derivative of the function is. So the second derivative will be what? 1 plus x squared to the minus 1/2 times 2x. Isn't that the derivative of the integrand? And I know something secret, that the second derivative turns out to be 1 plus x squared to the negative 3/2. I just happen to know that. Let's kind of see what we get. All right. So now, this function right here is 1 over the square root of 1x squared to the third. When I want to make this whole thing bigger, do I make the denominator smaller or do I make the denominator bigger? If I want to make the whole thing bigger, do you make the denominator smaller or bigger? Make the denominator smaller. What's the smallest the denominator can be? 1. And so in some sense then, the second derivative is going to have to be less than or equal to 1 on my subinterval 0 to 1. Okay, so that's good that we have that bound for the second derivative for that Taylor series term. What's going to be the length of each of my subintervals? Well, I have to figure that out. I have to figure out what the length of my subinterval will be. So the error of length n for the t of the trapezoidal rule of x is going to be less than or equal to h squared b minus a over 12 times m, where m is this maximum. So in other words, this is going to be less than or equal to h squared times 1 minus 0 over 12. And this is going to be equal to 1 over 12 n squared. Because each of my h's is going to be some subinterval. So I want 1 over 12 to the n squared to be less than 0.01. So that's going to imply, well, let's get everything out of the denominator. That's going to imply that 12n squared is going to be greater than or equal to 100. Or 100 over 12. What is 100 over 12, roughly? Lauren, you have a computer out. What's 100 divided by 12?
100 divided by 12 is 8.3b. So
8.3.
8.3.
N squared is going to have to be greater than or equal to 8.33. Okay. And so n is going to have to be greater than or equal to 3, right? So I need 3 points. Somehow I messed up my arithmetic here on this page. How did I do that? Oh, what is the square root of 8.33 then? That's where I made the mistake. .7 or something?
Yeah, 2.88.
2.88. So n should be 3.
Maybe just that.
It was. I'm not sure how I got n equals 2. A different day I get a different answer. That's not good. So I want 3 subintervals. Yeah.
How did you go from this step where you said h squared over 12 to 1 over n squared? Or 1 over 12?
Yeah, because h is equal to b minus a over n. Since b minus a is 1, then each h is worth n squared. Okay, so we can approximate this with taking 3 subintervals. So our interval could be 1/6 Because now our length of h is b minus a over n, or 1/3. So 1/6 square root of 1 plus 0 squared plus the square root of 1 plus 1/3 squared. So get ready here, Lauren, to calculate this. Make sure that I'm okay. I have to put the weight here as 2 plus the weight here of 1 plus 2/3 squared plus the final one, 1 plus 1 squared. Then divide that by 1/6. So I just have to evaluate it at these 4 points, and I believe I get 1.154. So what I would say then is that my error, since it's less than or equal to 0.01, would be 144 is less than or equal to the integral of f is less than or equal to 1.164. Is that what you got by this whole thing? 1.154 something else. So this process allows me to kind of identify the error and control the error, and to see how many terms I need to use. Okay, so that's just kind of the process you go through for trapezoidal rule. You know, you've got an integral, you want to get in a certain amount. If you know if you can bound the second derivative, you can do that. If you can bound the fourth derivative, that's even greater because you can use Simpsons Rule. Okay, now let's go to Gauss. Every undergraduate math class has Gauss and Euler in it somewhere, and this is where Gauss comes in again. What we're going to do is not equally spaced nodes, better nodes. This even goes back to our G project, right? You don't have to use equally spaced nodes. Maybe what we need to do is use better nodes and weight those differently. And so this was Gauss's idea, or it could be other people's ideas. But, you know, your weights in trapezoidal rule is like h over 3, 2h over 3, 2h over 3, h over 3. Or if it's Simpsons Rule, it's h over 12, maybe 4, h over 12, 2h. I mean, something like that. Those are the different weights you use to get a good approximation. But maybe, just maybe, there are better ones. So here's answer 1. Where do the weights come from? The weights could come from our Lagrange interpolation formula. So these would be the cardinal functions. So what we'll do is we'll integrate each of these cardinal functions, because they're polynomial that we kind of approximate it. Could be the y value times our cardinal function to get a polynomial which interpolates the points. Does that make sense? You've got y values, and then you're going to interpolate a polynomial through those points. And what we're going to do is have these cardinal functions be the weights. And so let's suppose that we have f of x to be equal to this, and we integrate both sides. We've got a sum of integration, and now we can take the sum and integration and replace them. And now if we integrate these, this will be our weights for our integration formula. Okay? So let's take an example. We've got the interval -2 to 2, and let's find weights. The nodes are -1 to 0. Again, 0, 1, whenever 1, 0, we get 1/2 x times x1. We integrate it, we get x to the third. Here, my x value is 0. My 1 value is 0. So x plus 1, x minus 1, integrate, and I get negative 4/3. And here, my third node is 1, x plus 1, x minus 0. Simplified this, integrate, and I get 8/3. So these now will be my weights at these particular nodes on the interval -2 to 2. Okay? Now, let's go ahead and check against the four functions 1x, x squared, x cubed. Here my weights are 8/3, negative 4/3, 8/3. So this is the true answer. And here are the function values. I plug in, since my first function is 1, I plug in -1, I get 1. I plug in 0 into my function 1, I get 1. I plug in, you get the idea. Okay, this is the true answer. If I integrate from -2 of 1, I get 4. Still, I'm thinking in math stats, uniform distribution, all that stuff. And so now I put in my weights. 8/3 times 1 minus 4/3 times 1 plus 8/3 times 1. Add that all up together for 12/3, 4. Okay? Now let's put in -1, 0 into the function x. -1 in for x is -1, 0 in for x is 0, 1 in for x is 1. Okay, the integral of -2 to x dx, because it's an odd function and it's equally spaced on both sides, is 0. So let's put it in. 8/3 times -1 plus 4/3 times 0 plus 8/3 times 1. I get 0. Those match up. Okay. Let's now try it for x squared. I put a -1 in for x squared, I get 1. Put 0 in for x squared, I get 0. Put 1 in for x squared, I get 1. If I integrate this one, I get 16/3. And if I do 8/3 times 1, negative 4/3 times 0, 8/3, I get 16/3. All right, let's try the third one. What happens if I put a -1 into x thirds? -1. F of 0 is 0 and 1. Well, so we already did this story before. We get 0. And if you integrate x third over the subinterval, you get 0 again because it's an odd function. So it checks up to x to the third. But now if we go to x to the fourth, 1, 0, 1, this integral is 64/5. And when we integrate this, putting this into 1, 0, 1, we get 16/3. And 64/5 is not the same thing as 16/3. So Lauren, tell me how much I was off there by 64/5 minus 16/3. I was off by, let's see, 5 point something. Ooh, a little bit more.
7.5.
Okay, so I was off by quite a bit there. However, I used equally spaced nodes, didn't I? Maybe I should use better nodes rather than equally spaced nodes. Okay? So that's the next one. And the idea with this, we can approximate any function just by evaluating the certain points. And sometimes this is more accurate with less work. I like that. I like trig substitutions, but boy, it can get long and complicated. If I just put in the right nodes, I can get a more accurate answer. So are there other possibilities for weight? And the answer is yes. Use special placement for the nodes. And this is what's amazing. With arbitrary nodes, n nodes will give examples up to polynomials up to degree n. So if I have 5 nodes, I can do polynomials up to degree 5. There we had 3 nodes. We did everything up to degree 3. Once we got to degree 4, we didn't make it. But Gauss, being Gauss, he said these nodes that we can give accuracy up to degree 2n minus 1. So if we do 5 nodes, we can be accurate up to degree 9. And since polynomials approximate a lot of functions pretty well, we can approximate other functions pretty well as well. This is just amazing. I mean, I'm just amazed already with the fundamental theorem of calculus. All we have to do is evaluate 2 points, and we get the whole integral. Now we get exact answers just by, we can't get the antiderivative, just plugging into the integrand and getting the answer. Okay, so let's go ahead and see that. So it's great. Where can I get these Gaussian nodes? Well, something you have to know is something about the function itself, the integrand, through some experience. But let's go ahead and try this. And what we'll do is we'll need some sort of function q, like we had for the cardinal functions. We'll need it to be a polynomial of degree n plus 1. And so what we're going to do is select the nodes of x0 to xn to be the blank of q. Any suggestions what the blank of q, what could go in the blank? It's a common phrase we use in this course. Any ideas? You just guess. I mean, it's not.
Coefficients.
Oh, pretty good guess. Good guess. Not quite correct. That was a good guess. Any other guesses?
Roots.
The roots. That's very good. Roots. Very good. Yes, we'll do the roots of q. And even as someone from southern India, he said ooh rather than for roots.
I'm from Indy.
I know. India is not quite southern. It's kind of like the dividing line. Actually, State Road, or U.S. Road 40 is kind of, to me, if you live north of 40 or south of 40. And plus, both ways are fine. Saying roots and roots are both fine. Okay, so we're going to select the roots of q. And then we're going to let the weights be the integral of this cardinal function times f of xi. And it's going to be exact from polynomials up to degree 2n minus 1. Exact. And this is called Gaussian Quadrature. I don't know if you remember this from problem solving, where you talked about the loon and how they were able to take the same area, which is kind of the motivation for the compass and straight edge functions about doubling the cube and stuff like that. So, but there are other Gaussian forms to approximate. Like if you're in physics and you have a lot of e to the negative x terms, or square root of 1 minus x squared terms, or e to the minus x squared terms. But we're just going to start here on the easier functions and to show you how this is done. Okay, let's determine the Gaussian quadrature formulas with 3 Gaussian nodes and 3 weights for something in between -1 and 1. So we must find q. The degree of q will be, pick a number between 1 and 5. Hopefully you'll pick the right one. Do you remember what the degree of q needs to be? It's either n minus 1, n, or n plus 1. N plus 1, very good. So the degree of q must be 4. I'm sorry, 3. we need degree 3. So what we're saying is that the form of q is going to be some polynomial of degree 3, but it must satisfy that we integrate q of x times 1 of dx is 0, x times q of x dx is going to be 0, and x squared q of x dx is also have to be 0. Okay? Oh, because 3 nodes means n is n plus, because you start to 0. So actually we have 2 subintervals, and so we need 3. So you always start, we're in computer science where the first point is 0.
Okay, so if we have 3 nodes, you're saying that has 2 subintervals?
Yeah.
which
Yeah.
means we need one more than that for the
So a degree 3 polynomial.
degree Q.
Yeah. Okay, here we go. So what we're going to do is set C naught and C2 equals 0, then Q is odd. And so we get set C1 and C0. So now we're down to C1x plus 3x squared. Because if we do that, then Q is odd. And this integrate against x will be 0. And x squared against this will be 0. Because this is actually a third polynomial. So this is an odd function. Over -1 to 1 will be 0. And if you multiply by x squared, this is x cubed and x fixed. So it'll still be an odd function. And so integrate from -1 to 1 will still be 0. All right, we got to find C1 and C3. So if we integrate x against C1 and C3, we integrate and integrate, evaluate it, and we get 2/3 C1 plus 2/5 C3. So we're down to this. 2/3 C1 plus 2/5 C3 is equal to 0. We get our choice or our option of what we want to do. We've already cut down this from C0 is equal to 0 and C2 is equal to 0. So now we just have to choice between C1 and C3. And we get a lot of choices here. I'm going to make the choice because I'm the instructor. No, I'm giving the choice because this is what other people have decided to do. And so they decided to set this equal to 0 and let C1 be 3 and C3 equal to -5. I'm sorry, -3 and 5. In that case, you get -2 plus 2 is 0. So here is my polynomial that Q of x is 5x to the third minus 3x. And that's going to be my Q function. That's going to be my weight that I have. So its roots, you can use Newton if you want to, but its roots are 0, negative square root of 3/5, and positive square root of 3/5. Those are going to be my weights. Or, sorry, not my weights, my nodes. So now let's find the weights. I have to have this to be exact. Okay? So if I integrate from -1 to 1 of 1, what's my integral going to be? Again, a nice uniform distribution. What's my integral going to be from -1 to 1 of 1? 2, right? Width of 2, height of 1, get 2. And so the right-hand side function will be a0 plus a1 plus a2. Okay, so this has to equal 2. And then I put an x. Again, this is an odd function from -1 to 1. I get 0. And I plug this in, a0 times negative square root of 3/5, a1 times 0 plus a2 times square root of 3/5. So these two things have to be equal. And then x squared is x cubed over 3. Put in a 1, subtract it if you put a -1, you get 2/3. And you plug x squared, plug your values in x squared, and you get 3/5 plus 3/5 a2. So now all I have to do is solve this for the weights. Just a reminder that 10 o'clock tomorrow are 2 math seminar talks. this is the time for a couple of you who are not in the class to pick up some other ideas. I guess tomorrow's is not as much about modeling, but the following week will be about modeling, and you should go. Okay, so we just have to solve these three equations, three unknowns. And if you solve those, you get the following weights. You get A naught is equal to 5/9. A1 is equal to 8/9. And A2 is equal to 5/9. And so with these three weights, I can evaluate any polynomial between -1 to 1 exactly up to a certain degree. So up to quintic polynomials, I'll get an exact answer. All I have to do is evaluate the function at these 3 points and weight it this way, and I'll get the exact answer. 3 points, exact, 5th degree polynomials. Great.
Can you go up to the chart again? Can you explain it one more time? Because I was a little bit lost in what you're doing.
This one here?
Yes.
Well, what I do, I need to find the weights. And so what I'm going to do is integrate over 1x and x squared.
Okay.
And find that value if I integrate from -1 to 1.
Okay.
And what I have to do is I have to have these weights equal this exact answer.
Okay.
So I put in my -square root of 3/5, 0, and square root of 3/5 into these functions. And then evaluate, set those equal to each other, and that will find my weights.
Why does it have to be exactly equal?
Because I want them to be exact on 0, 1st degree, and 2nd degree polynomials.
Okay. But it turns out it's actually exact up to quintic.
Exact up to quintic, yeah. Okay, now the one difference is that what if you want to integrate on a different interval? So let's say you want to do from 3x squared dx on 0 to 8. What you have to do is you have to do a translation of variables and get it from 0, 1 to -1, 1. And so you translate it -1 to 1 over this one, and then you use Gaussian quadrature. Basically, it's setting up the slope. When x is 0, you want t to be -1, and x equal to 8, be t equals to 1. There is actually a formula in the book. You don't have to do it this way, but this is kind of how I think about it. Yeah, Rachel. Or Raquel.
That's how you figured out t is just by.
What was that?
You figure out t just by wanting it to be between -1 and 1?
Yeah. And so if that's the case, you've got the point -1, 0 and the point 1, 8. And so you figure out the slope and you get the equation of the line. X is 4t plus 4 and dx is 4 dt. So you can then substitute for x what it is in terms of t and dx what it is in terms of 4 dt, and then go ahead and use Gaussian quadrature. So again, it's a calculus 2 idea, just a little bit extended a bit. Calculus 1 idea? Definitely a calculus 3 important use of that. So that's the formula that you can use. What your values are in terms of x. So 2x minus b plus a over b minus a, and then you substitute this in for x, and then you just have to put b minus a over 2 in for dt. Now, your book on page 646 on table 22.1 has all the Gauss notes. I wish they'd given the exact answer. That's why I'm going to tell you to go to Wikipedia. And if you go there and you scroll down, these are all the nodes. that you could have for the interval -1 to 1. Okay, so it gives you both the exact answer and the approximate answer. And you can then use that to approximate. You don't have to just approximate polynomials. You can approximate any function pretty well. There's also one at Wolfram World, or Math World on Wolfram, that is also beneficial. Here's what they say, and engineers, can't you give us some exact answers? You don't always have to put everything in decimals. Okay. And you can extend this to any positive function so that it works. So you still could have the weights of this, instead of just the cardinal function by themselves, you could have Li times the weights. And that's why you get some other things like the Chebyshev polynomials coming back again. You can have quadrature, and that's how we could have approximated that Runge function, or pathological example, why you just don't want to add more nodes. The error gets worse. Your weights turn out to be pi over n. And then if you evaluate those, it spreads out the error, and you can approximate it just by evaluating the function at those points. As long as you have the function, you have the square root of 1 minus x squared as a separate thing. You factor that out and then use it on the function that's remaining. Okay? But you can do some other ones. If you have infinite limits, there's actually Lagrange quadrature. Like if you have some sort of function times e to the negative x, which is pretty common in chemistry and other things because you have a decaying function, just factor out the e to the negative x and then have f of x, and then you could use the Lagrange polynomials or even the Hermite polynomials if you can weight out the e to the negative x squared. And just evaluate at several points, get a good approximation. Everybody's happy. So, for example, if you wanted to use the Gauss quadrature on e to the negative x squared, from 0 to 1, our first standard deviation, area of first standard deviation, although we don't have 1 over the square root of 2 pi, so it's not going to be the norm CDF. We put the 1/2 t plus 1/2 in there. The derivative is 1/2 dt, so we got to put the 1/2 in front. Evaluate at 5 ninths, 8 ninths, and 5 ninths. You add all those points up, and you get 0.74681. And the T89 that I used was 7.682. So you got four digits of accuracy just by evaluating it at 3 points. And if you look at Mathematica, they say, how do they integrate it? They say to use quadrature formulas. And so this is the big reason to understand this, because how your calculator and how computers get approximate answers for integration, they're using these quadrature formulas to do so. And a better way to find the nodes is maybe use Legendre rather than 1x, x squared. You could use the basis 1x, 2x minus 1. And anyway, use those for your nodes. Those actually work much better. And you can find these using a recursion relationship. Yeah, it's just amazing. Now we pause because we're now even going to move into something that will even be able to do more for us. Okay, and this is called Richardson and Romberg integration. We used to have this thing called, you put into your fuel tank, it was supposed to inject it and make it go faster. I don't know if Lucas Oil or STP, or I think I read somewhere they're all kind of hokey, but I just need something like you put it in and you just explode and so much more. It's sort of like giving Popeye spinach. Do they still have Popeye commercials? Cartoons? No? Well, all right. Something that kind of energizes something and makes it better. All right, so here we go. Here is Richardson extrapolation. Here's the idea. If we have an interval with n intervals and we estimate it with 2n intervals, what I'm going to do is weight this average. I'm going to put 2 to the p on the 2n intervals and subtract from the 1 interval and then divide by their weights, 2p minus 1. Because if I take I minus in, I should have some constant times n to the p. This is like OH squared, or OH to the fourth. So for the trapezoidal rule, I have p equals to 2. And for Simpsons rule, I have p equals 4. We're going to use the weighted average to our example. Like if we had Boole's rule, which is OH to the sixth, p would be 6 in that case. But this is kind of the idea that we're going to use, because if we're saying that I minus n is some constant over n to the p, like OH squared or OH to the fourth, I'm going to weight this to get even another better answer from this. So let's kind of work with an example where we know the answer. If I integrate 3x squared, I get 512. And let's suppose I do n equals 2, which means if I have n equals 2 from 0 to 8, the length of each subinterval would be h equal to how much? 4. And if I have h equals 2, how many subintervals do I have? 4. And if I have h equals 1, I have how many subintervals? 8. So if I go ahead and use the trapezoidal rule, 0, 2, 1, put in 4 squared times 3 is 48, and I get 576, which is not so good as 512. If I put h equals 2, I've got 2, 2, 2, 1. 3 times 2 squared is 12. 3 times 4 squared is 48. 3 times 6 squared is 108. And 192, I get 528. And if I do the same thing for T8, I get 516. So I'm not getting the exact answer, but I'm getting closer. Okay, now let's show you how we might use the Romberg here, or Richardson, either way. So what I have here is that p is 2 because trapezoidal rule is OH squared. In our example, n is equal to 2. So what I'm going to say is R4 is going to be 1 over t squared minus 1, t squared I4 minus I2. Because this is the more exact answer, I'm going to weight this more than the one here, the lesser one. And so what I'm going to get is R4 is 1/3 times 4 minus 1. So if I would have used Simpsons rule n equals 2, my subinterval is length 4. H over 4 is 4/3, 0, 4, 1, because, well, 0 I put in there, I get 0. So 4 times 48, 192, I get the exact answer. But if you would have used R4, you could have weighted 1/3 times 4 times 528 minus 576. I get the exact answer as well, and I get 512. Oh, and so we will end it on that kind of idea. And we will derive the Richardson example a little bit later, but it's an example of you use something evaluated previously to what you evaluated now, weight that average, and you get leaps ahead of whether you just would evaluate the next one. Okay, but it works now. You can find the Blackboard site for the homework then. Okay, a lot of calculations. You might want to use Excel to figure out your values. Just consider. Okay, have a good Monday. May God bless you today and keep you, and have His face shine upon you and give you peace.